Alrighty, hey there folks, welcome to Module 2 of your Introduction to Non-Interactive Rendering Techniques, and we're going to dive into this module, and you have your first assignment out. So I just want to point folks again where that first assignment's going to be on the assignment's calendar, so it's A1 here, and the due date here is marked as July 16th, so that gives you about a week to get started, and I'll be checking in with folks and sort of updating office hours if you need any help. So with that said, I'll revisit the homework by the end of the lecture, but let's go ahead and jump into today's module. All right, for today's module, we're going to talk about image generation and a few math notes here. So I'm going to hop into the slideshow, and I'm going to go over to slides and enter the slideshow here. And by next week, you'll also want to make sure that you complete the in-class activity. So I'll leave that here as a reminder here. You'll just open this and then click on the in-class activity link, and then whatever the activity is, just complete the survey, submit it, and you'll be good to go. But let's go ahead and dive into the slides here. So what I've got for us, as I always like to do, is start up with a little bit of a warm-up. So as mentioned last time, this course is going to be talking about ray tracing. And there's a fun prediction by this gentleman, Morgan McGuire, who's a professor at Williams, also works at, has worked at NVIDIA, and now works at Roblox, as well as many other places. University of Waterloo, I believe, is his permanent appointment. But he's been one of the sort of leaders in computer graphics, both in academia and in industry, which gives him a pretty unique perspective. And he says by 2023, ray tracing is going to be essential. And he's talking primarily about real-time applications, which we'll discuss by the end of the term. But it's pretty cool to know the stuff that we're learning here is a little bit ahead of the curve. So we're a little bit ahead of the future. He made this prediction all the way back in 2018, and it's been proving to be true. Thus, why we have a dedicated course on this now and are trying to just keep up with the times. Some other things to note is that his book, The Graphics Codex, is also free. It'll be one of the resources that I might occasionally link to, and Morgan's just someone to know about in the industry. So just wanted to introduce that kind of fun prediction and just show us that you're on the right track for being in this class. All right, so let's continue onwards here. So last time we had our introduction to the course through the course website. We got to figure out some things, some administrivia, how the course is going to be run. Again, for those who have taken previous classes, this is going to be very familiar stuff. But for those who are new, welcome, and hopefully you're acquainted, and please follow up if you have any questions about anything with the course. All right, so course logistics-wise, some things coming up. Again, assignment 1 is going to be in your repository. You'll need to do a git pull to retrieve that assignment, and I'll show you how to do that right now, actually, because I go to my monorepo here. And if I look at the state of my repository here, I'll see that there aren't any folders or anything in here indicating assignment 1. So what I need to do is I need to do a git pull. Type in my password or my token here. And it's going to pull all the new directories that I have uploaded. So there's a directory for assignment 1, and I've also pushed another folder with just common objects and things. So that will be used throughout this class. So now if I look, you will have assignment 1 in your repository here. And you can move into assignment 1 and go through the README or read through the parts of this. Now this will be a little bit easier to read these documents on the online GitHub, but you of course have them here available as well. So I'll jump into the assignment towards the end of the class once we talk about today's topic, and it'll make a little bit more sense. Okay, so that's just the logistics, how to retrieve the assignment and how to get started. And just as a reminder for folks, if you're just joining in otherwise, to get the course repository, please just click on this link here for the course monorepo. It's on the schedule here, and that will invite you to the assignment. So now if I click on this, it'll ask you to accept an invitation. If you've already accepted it, then you'll just click on the link here, and you'll see where that assignment is in assignment 1 and so on. So I'll leave this up here just so you can, we'll revisit this in a few moments. Okay, let's continue on with today's topic. So obviously we're recording here, and a few takeaways from today. We're going to be talking about color, image formats, and just a few notes on math to get us started in this class. So sort of a warm-up for us and a nice programming assignment to get us acquainted to everything computer graphics. All right, now where I want to start with this class is first talking about the subject of color, something that you're probably familiar with from the start of your education where you talk about colors. But before we start jumping into all the mathematics and all the other different things involved with ray tracers and rendering techniques, we need to understand a little bit more about how color works and how it's represented in the computers. Because our goal is going to be to generate some high quality images. So we want to know really how color plays into that, how we store our data, and just a few other things to give us some intuition about how color works. For folks who have taken computer graphics with me, we didn't do as deep a dive. Maybe if you've taken graphics with someone else, you did a little bit more, but it is interesting to know a little bit about the science of this. It's a whole area. You can do a PhD in it. For folks who have done design courses, maybe some of this will be familiar. And of course, everybody in this class may, whether you realize it or not, realize that colors in different cultures and so on evoke different emotions and play a really important role in how things are marketed, whether that's a game or a product, okay? So anyways, when we start with color, I want to start with first talking about light, okay? So light is a form of electromagnetic radiation that we can see in our eyes. It's what we can perceive as humans. Now, other animals, bees, and things can see different types of light on or different types of electromagnetic radiation, but we see what's on the sort of visible light spectrum, right? The sort of Roy G. Biv, red, orange, yellow, green, indigo, violet, these colors. That's sort of the acronym for this, but this is what we can see or perceive as a human, okay? And the way that light works is it's actually, as we've found out, or I suppose was proven by Einstein and some of these other folks about 100 years or so ago now, that light travels in waves. Okay, so the light's moving along in a wave, and the result of the light moving in a wave and then some sort of magnetic field, like for instance, it could just be Earth's magnetic field, it results in a vibration, okay? And that vibration, or how it's vibrating, or how that wave's moving through air, in our case here on Earth, creates a wavelength. And depending on what that wavelength is, or how often this wiggles, that's what generates a color that we can perceive, okay, in our photoreceptors or our eyes, okay? So that's what's sort of going on behind the scenes when we think about how light is moving. And again, it's going to be helpful to think about light moving or sort of propagating in this line. It's a wave, but it's sort of wiggling in a certain pattern to indicate color, again, that we can perceive. Okay, so here's just kind of a cool example of this. If you've ever seen a prism where you shine a white light on it, and then it's sort of the light as it's shining in, if you shine with a flashlight or just a general light source in the world, it will break up the colors into each of their sort of channels, or scatter them, because as light passes through different materials, in this case a prism is glass, this is a rendering of it, the different wavelengths will scatter at different rates, or another word for scatter is they'll refract or be bent to different degrees, and based off of how they're bent, that's what actually gives you this prism effect, where you look in and you can see all the colors of the rainbow. It's the same thing that happens when you see sort of a rainbow outside. The light's being bent because it's passing through something, usually a cloud or the air, in a particular manner that scatters the light coming from the sun to produce this sort of interesting or beautiful phenomenon, okay? Now this is something that we're going to also think about too when we're modeling how light's passing through surfaces and what those the sort of index of refraction is for various materials. So we'll have to actually model this in various materials, but again, this is where the intuition comes from. Okay, so how do we perceive these different colors? Well, our eyes are able to help us with this, us versus other animals or creatures. We have specific photoreceptors that can pick up or sort of discern different colors of light. Okay, so we have two types of sensors really in our eyes, or the two most important, I guess, are rods and cones. You might have heard of this, but rods sort of help us with our night vision. We can sort of detect things. We can't really see color with them, but if you were walking around at night, you would be able to probably perceive things in sort of a low light situation, or identify that there's objects in front of you, maybe in sort of a grayscale-ish manner, but you want to be able to see what the color is. And that's what your cones are responsible for in your eye, actually being able to, as light enters your eye, particular cones, it's estimated you have around a few million of these, activate or sort of light up and send a signal to your brain to help you, again, perceive what that color is. Okay, that's kind of a cool system here. Okay, now what are those colors coming in? We sort of have these cones, red, green, and blue, that help us detect light. But you're probably used to, maybe you learned the primary colors, again, in school, depending on when you went to school, as red, yellow, and blue. And those combination of those primary colors could make up any other color. Okay, if you combined red, yellow, and blue in different combinations, you could retrieve a certain color. So just from these three sort of primary colors, you could do that. Now, depending on what type of medium you're using, meaning digital or print or paint, there's different sort of primary color systems. So your color wheel might look a little bit different. So you can see that there's a bunch of different systems listed here, and you have your primary and sort of secondary colors. So the two that I want to discuss as far as color systems and representations of color on machines are CMY for cyan, magenta, yellow, and the K is for key, and then RGB. Where this is red, green, blue, and then red, green, blue, and alpha. Okay, these are primary colors of light. Okay, and we're talking about primary colors of light as opposed to painting, because that's sort of what we're working with this idea of rays and light sources, and what colors our eyes can perceive. Okay, we're interested in light and electromagnetic radiation on the visible spectrum. Okay, but we want to talk a little bit still about some of these other models, just so you're familiar: cyan, magenta, yellow, and the difference, and why we're going to use RGB to talk about color, if you've ever wondered. But they're different models primarily for the type of medium that you're going to be using. So CMY is what we say is a subtractive model. That is, your colors are created by absorbing wavelengths of visible light. Okay, and this is sort of strange. You're absorbing something, so subtracting it away, meaning that as light enters, the wavelengths that do not get absorbed get reflected back. Okay, so this sort of makes sense because you're laying ink on a paper for things you want to absorb, and then the color that you reflect back is, well, none of the colors that were absorbed are laid out onto the paper. Okay, so that sort of, again, makes sense that they use this, or think about this sort of cyan, magenta, yellow color system, okay, or this sort of color model. K, again, is for key. There's a little description of what that is, but that's basically what you're subtracting from the color. So from black here in this sort of model, what's being absorbed and what's reflected back. Usually people just say CMY, and K is usually just black ink. Okay. So again, the model that we use, though, in computers and electronic devices in general is the RGB model, okay, for red, green, and blue. Okay, so these are the three sort of primary colors of light, and these are the sort of three individual color channels. So color, again, is broken up into these individual channels: red, green, and blue. So you can see sort of all the red light being reflected back here, all the green, all the blue. Maybe you've done one of these experiments where you put a filter over a light that's a red filter, green, or blue, or whatever. And you've seen this sort of experiment, but this is rather just the raw image that is only taking out the red components and displaying it on the device here. Okay, so you can actually see what's happening, and when you combine all of these, then you get your colored image here. Okay, so let's continue on. Now, how do I determine how red something is, or green or blue? Well, each of those channels has a intensity value associated with it. Okay, it's usually ranging from 0 to 255 on most systems. Sometimes you normalize it, so it'll be 0.0 to 1.0. But that's just mapping the values as decimals. But 0 to 255 is usually the range. And you can see in this sort of slider, or this dial here, as you add more blue with a full red, you get a sort of purplish color or indigo. As you increase all the intensities up to 255, you'll get a white light. If you just have green and blue, you get sort of the sign. If you just have green as the most intensity, you get more of a green image. Okay, so that's how it works. Again, it's an additive model where you're adding in these intensities to generate the light or the color. Okay. Now what this is actually doing, or what this is a model of, this is actually an LED, so a little light here that's being modeled, and you have a red source, a green source, and a blue source, and you're figuring out how much of that component to output from the LED, and that is what your final color is. So here's just sort of the schematic, and here's another view of it with the colors. And this top window here is, playing around with a slider or a color wheel if you've worked in Photoshop or any of these applications. Okay, now there is another part to color that's worth mentioning, or it's going to actually be a very important part of it, but it's the opacity, or the alpha channel. It's the A, the RGB, and then the A portion of the RGBA model models how opaque that particular color is, meaning how much can we see through it. So if the intensity A is all the way up to 255, that means it's usually fully opaque. If it's 0, that means it's something we can fully see through. Then anything in between that is some sort of translucent material that we can partially see through. So this is going to become useful when we want to layer objects on top of each other, or just model certain phenomenon like a prism, for example, a piece of glass that you can mostly see through. It's mostly translucent, but if you use sort of this example, I'll bring myself with the screen here, where I have a glass, right? You can see through that it's a glass, but there is some, dark color here. So I can see through this. I've got a little bit of water, so it looks sort of interesting, which has its own properties that you'll have to consider when we do our ray tracing. And soon, by the end of this class, you're going to start looking at objects like this and thinking about graphics, which is kind of fun. But anyway, you get the point that it's not fully opaque, right? You can still see through it a little bit and understand that this is a glass and so on. So anyways, that is something we also want to be able to model and store as part of our image data. Okay, and then this is a part of color and blending colors together. So you can kind of see how this works. So look at this first diagram here where I have an opaque A and B object. Well, you'll just draw whichever one's sort of on top of the other. But if they're partially transparent, you can see where they sort of blend together at this intersection point and create a new color there. Okay. All right, now with that issue of transparency, especially with transparency and layering, but also true of just colors in general, there is one issue of gamma correction. So this is something that we're actually going to need to do in our images. And what gamma correction is actually doing is it's sort of making the image pop a little more. Because what happens is our eyes are actually really sensitive to color. We're pretty visual creatures. We're pretty good at detecting change visually and using relying on our visual systems to detect changes. So you'll notice a subtle difference here if you look at where I'm highlighting towards the middle of the screen. This blue here versus the blue down here. And there's a subtle change here where you can see that I'm blending in this blue here with the red, and you can see almost more colors here. Whereas this, it's a little bit more of a hard, it looks like there's just a sort of 3 colors here on the screen. Like a little bit of blending towards this side, the middle is darker, and then the right side's fully blue. But we're actually blending this in to get a nice sort of gradient here. Okay, so there's something you can do called gamma correction, which helps you or rather, the image that you generate will better show what you as a human would see in real life. It's distinguishing a little bit better the color change or the transition. And this is very common when we're blending things together. Here's a nice sort of interactive example you can do. I'll open up this here, but you can see, how we perceive things. So here's sort of the reference. Here's what the image looks like, and then you can see how the camera sees it versus how our eyes see it, and sort of go back and forth here. Okay, so our eyes are sort of the true picture, but what we can represent is sort of here. So it's sort of a hard correction here. Okay, so we have sort of the actual luminance here by how we're perceiving things versus the camera. Okay, so if you've ever looked through a camera, or when you watch something, if you watch something in real life through your phone, and let me bring myself back in the screen. Let me see if I can do this reasonably here. One moment here. So I'm going to do this sort of experiment here. So I've got my camera here, and if I'm looking at myself through the camera here, and let's see if I reverse it and you're looking at yourself through the camera. Now there's going to be a green screen. It's going to be a little bit weird. If you look at the image of me here, it's a little bit harder to see. You can at least tell that it's not as correct. There's some issues going on with the reflection and stuff, but it's not as sharp as what you see. And gamma correction is one of the things that can help with this. Okay. So what's it doing? Well, if we look at this curve here, you can see that the actual luminance with our eyes, see how it's this sort of nice, smoother curve here, versus what our camera captures is just sort of these very discrete steps in the actual images that we capture here, okay? So let me just show a few examples. We'll actually implement this. There's actually it's not something that's going to be a super complicated algorithm. In fact, if you do the reading listed from today, you'll actually, it'll help you complete your homework, and it'll talk a little bit about gamma correction here. But basically, there's a little formula that you can apply that would take an image like, let's see, here's the original here, which again looks pretty good, but you can sort of control for, how bright or how dark you want this image to be. And again, I guess it depends on what you're trying to show here, but something around like 1/2 like this probably shows closer to what you were actually seeing, right? If you were actually underwater looking at this image here that was captured from the camera, maybe you were able to discern from some of these things a little bit more. Now you can sort of overcorrect for this as is done here by really increasing the gamma, or really sort of undercorrect for it and lightening the image. But it could give you a different effect. So again, this is something that people are going to play with a little bit in Hollywood, perhaps in a movie, but we also might play with it just a little bit to give us a closer depiction of what we really see in life, and trying to get our computers to show us what we as humans saw in real life to make the image a little bit better. So in some ways you have to play around with this a little bit, but you can see from the original image, and you'd have to actually be there to tell me which one of these is correct. Maybe there's a flash or something on this image, but that would be the idea. Okay, but wait, there's more to color here that yet we have to talk about, and color models. So we've discussed the sort of cyan, magenta, yellow as a sort of color model or a way to color things. But there's also, and then red, green, blue, but there's also another color system that scientists have created. Now, I want you to do a little experiment and pause the video and see if you can tell me what colors, or are tiles A and B different? What colors are they, or are they different? And if you've paused the video and taken a moment to discern this, you can actually use a color picker tool if you copy this image into a program, or I've borrowed this way to show that you can just draw a rectangle that's the same color as A here. Just draw it down here, and you'll see that when you overlay it, they're actually the same color, right? When you overlay this, it becomes very clear that they're the same. But when we're perceiving this, this looks like a white tile here. Now there is a shadow that's being cast here, but you know, our perception of colors as humans is actually affected much more than by just the color intensities. That is just the red, green, and blue values. So this is kind of a neat experiment here, where again, because there's a shadow here, but when you're contrasting against shapes that are next to it that are actually darker, you know, these don't. Now, is this originally a white tile? Yes, it is. But under the shadow, it's actually the same as another tile here. So it's kind of cool. And the phenomenon here is that we have to also consider hue, saturation, and brightness here. Okay, which is sort of a thing that takes us back to this photo that went viral a few years ago. I think it was around 2016 or 17. So maybe you're familiar with this. And some of you are going to see this as different colors. So I'll be curious. Go ahead and post on Piazza what colors you see this as. I see this as gold and white. That is in contrast to Taylor Swift, who saw this as blue and black. So you can see which celebrity you match with if you click on this Wikipedia. But the reason for that, again, is because of the hue, saturation, and brightness. And, you know, I can't unsee what I see now until I see it as the other color, I guess. So let me know in Piazza if we differ, but I see it as white and gold, okay? So anyways, that goes back to this color model for modeling hue, saturation, and value, or sometimes brightness, HSV or HSB in this system. And this was actually a system created by some scientists, I believe in the 70s or maybe the 80s from Stanford, to actually help us just sort of understand color, and it matches a little bit closer to how we perceive things if we actually use hue, saturation, and value to draw out the colors. And there is a mapping from RGB to HSV and vice versa. But basically what these components break down to is that the dominant wavelength, that's the hue, so maybe it's sort of more red or more blue, you know, whatever those, going back to the, again, electromagnetic radiation and understanding what the wavelength is. And then the intensity, so how much of that color is it expressing? Is it a really dark, you know, is it really red or just a little bit red? That's the sort of intensity. And then the value, again, I guess, is the lightness and the darkness of the color. So how saturated or how full is that color? Might be another way to think of it. So hue, saturation, and value. Or hue, saturation, and then brightness might be a little bit for values. Brightness can be how we think about that system. Now, why don't we use it? Well, it's a little bit less intuitive, right? You can go in the wiki and read about it. If you're doing photo editing and stuff, it's often useful to think about some of these, right? To just take the sort of value attribute and use that to lighten or brighten an image. That's, you know, certainly useful to then think about it in that manner, rather than thinking about, oh, I have to make this a lesser green and then just dialing down green, but that would actually be changing the color in the RGB system. So hue, saturation, and value can be useful for actually editing the images and getting some artistic effect. Okay, and again, there is some mapping from HSV to RGB. You can read about it on the Wikipedia. All right, so now that we've talked about color for a little bit, I want to talk about, you know, how do we just store this? You know, talk about some of the problems and some of the systems that we can use, but how do we actually store color and images? And, well, minimally, what we need to do is store the dimensions of an image and then the colors of each individual pixel, okay, into our some sort of image format or somewhere where we can store it and keep that data, okay? Now, we have to sort of commit to a color model. We're going to commit to RGB in this class because we're working with light, but you would, again, do this in perhaps HSV or whatever system that you like, and you could store those values as well. But we're going to use RGB. That's sort of the standard, okay? And we need to pick some sort of format. So there's lots of different image formats. Here's sort of the ones that come to mind for how you can store images. So all of these have sort of different trade-offs and Just a few notes on these. Bitmaps are pretty universal. You've likely used it or saved an image as a bitmap. It's sort of uncompressed. It gives you a high quality image. It's sort of a standard for portably, exchanging images. JPEGs, on the other hand, these are your these are your compressed images. So they're really good for websites where you want to, when people visit, you want the images to load fast because they're smaller images. That means they're lossy, so you're losing some of the quality, but they're good again for sort of storage and so on. PNGs are also used to portably transfer data, but they're lossless, and they're useful because they also have an alpha channel. So people will use PNGs when they want to convey transparency. PPMs we're going to talk about in a moment. They're sort of a simple lossless format for raw pixels. TGA is another sort of format similar to BMPs. I'll just leave that as a note there. RAW is the sort of minimally processed pixels. These are usually what your cameras, if anybody, again, is doing photography with a non-cell phone or whatever, you're getting a raw image, so the actual just raw pixel data stored there, okay? No compression or anything. And then GIFs, GIFs, that's how I pronounce them, are popular for using as sort of animated images. I pronounce them as GIF, like gift, as opposed to GIF, but I guess it doesn't matter. That's a big debate in the world. But anyway, the data stored in each of these images consists of something called pixels, okay? Now, a little thing about pixels. What is a pixel? Pixels are not little squares by definition. So, if there's one thing to make you sound smart in this class, if you're talking to someone who's a real graphics guru, these sort of folks here, really you're just sampling an image, and the x and y, so you're sort of positioned in a Cartesian space. So where you are at position x7, y10, that's where you're sampling from, and that's the color. Now, it happens to be that that's going to be convenient for us to think of how we store things, right, in an array or some sort of data structure. For example, we would be using, or just, storing x and y positions of those pixels. But if anybody, asks you, a pixel is really just a space that you're sampling from a continuous image. So again, if I bring myself back on the screen, right, this is a continuous image. Of course, there's a finite sort of resolution that you can see on your camera, but technically in the world, we can keep going smaller and smaller and smaller down to the tiniest atom and sort of sample what that color would be. So anyway, that's just something to keep in mind. Pixels are things on our screen that we can sample from, okay? And that's related to the dimension of the image we're working with for our screen. So how many image pixels you have on an image makes up its width and its height. And again, the biggest monitor you have with the newest technology, you usually get more pixels. We say you have a higher resolution, and you can get sharper images. So you can be the judge down here comparing, a 1080p, which is HD, which I think still looks pretty good, but you can really tell the difference with the 4K for how many, the rivets and stuff in this sand here, which I wonder where it is, maybe Utah or somewhere. But anyway, you can tell it's a higher quality image here. Okay, you're storing more data, so you have higher resolution. Okay, so in practice, just thinking about this in programming, you're going to have some sort of pixel format that you save things in. Okay, and it's going to be RGB for us in this class. That's what we'll be using. I want to say 100% of the time, but most of the time RGB or RGBA, where we have an alpha channel. But you'll have some sort of structure like this. Again, the programming language is your choice. I'm going to show my snippets in C and C++. And again, where are those snippets? Well, anything that I add here will be in the module, and then under code samples, if you click on this, we're in module 2. So if you click on module 2, you'll find the corresponding file here. Okay, so you can take a look at that whenever you get a chance. Okay, so let's see. So something else to note about these, though, is the RGB, and again, this is going to depend on your language, but one of the reasons I like C or C++ for this course, as well as many other languages, is I can choose the data type. If I'm only representing ranges of data from 0 to 255, I just need an 8-bit integer to do that. And it's unsigned here. That's what uint8_t means. It's an unsigned integer for 8 bits, and that's the type. So that's the range. You'll see people use ints, and it's a little bit wasteful, for example. But if you want a little bit more precision, you can use a float as well. And maybe the range is still 0 to 255 where you're capping it, but you have decimal precision within it. Okay, so you're storing more bits per pixel here. I'll talk about this in a moment. Okay, there are tricks and stuff to just cram and sort of access 8 bits at a time in a 32-bit integer, and some of these tricks where you can bit shift. I don't care too much about this class. Maybe I'll do some examples if you like, or in my ray tracer. But you don't have to worry about that. So just having some sort of structure like this is how you can create a pixel. Okay. Now again, we said images consist of pixels. So what's the format look like? Well, we're going to look at one of the formats today for your homework. So pay attention here for your homework. This will be familiar for other folks who've taken graphics with me. Soon there will be stuff that's not familiar, don't worry. But we're actually going to be working with a format called the PPM image format. So that was one of our formats listed here. It's sort of a simple lossless format. That means you're storing the raw data. And here's what it looks like. So it's sort of a plain text-based file. That's one of the formats here. The first byte in the file is what we call magic number. Most files that you actually load on your computer have this sort of first byte to tell whatever program is loading it what the file format is. So that's how the data is structured. So I'll just say P3 when you actually parse the ASCII characters. The first byte will be a P, and the second byte will be a 3. That's how you know it's this file format. And then any of the other data that you load that begins with the hash mark or the pound sign is a comment. And then the next line is the dimension, so we know how much data or how many pixels we have. So this is 4 by 4, the width and the height. And then the next value is the range of the color, so 0 to 15. So we're representing our intensities, or the maximum value could be 15 here for our R value, our G value, or our B value. Okay, it could be 255. That's what it's most commonly is. This particular example uses 15 if you look at their documentation from the PPM folks. But usually this will be 255 for us. Okay, and then the next set of 3 values is the red, green, and blue intensity values at the first pixel. Okay, at position 0, 0. Okay, and then the next set of pixels, the red, green, and blue, and then the next set of pixels, red, green, and blue, and so on. Okay. So this is how you sort of interpret this, and then the rest of it's just the data, okay, for the image. Okay, so here it is all in one slide. Now, there is also another format of the PPM image. This is something new for former students and new for everybody, I guess. There's also a format called P6, and this is going to be useful primarily for iteration time. That's why I'm looking at it in this class. But what P6 is, this time if you read in the magic number, same sort of format. You have your dimensions, comments, the range or the maximum value. But the actual data here isn't just stored in plain text, but it's binary data. Okay, so the binary data is a little bit more compressed. Why is it more compressed? Well, we're not storing a space character or new lines or any of those characters there. So we're actually just going to store the rest of this file. It's going to look like gibberish, but it allows us to sort of write images and read images faster, because we could just read them all as a single blob of data, or we can make an assumption about the data that's stored in it. We don't have to assume that there's spaces or new line characters or those kind of things to parse out. So you will be actually working with the P6 format a little bit here, and you can test it out by seeing if some program I like using, and let me go ahead and just open up here, the GIMP program. And you can actually save out, let's see, I've got to my file here. Let's see if it'll do it in a reasonable time. Let's export it out. And if you want to look at the different formats here, let's do export. Oops. And if I do it as a ppm, and it's selecting by the file type here, so you can see all the different file types here. It's going to list it as PBM, I guess, here, but let's do ppm. Oh, here it is, actually, ppm. And when I export it, I can either do it as the raw, and that's the binary format, or the ASCII, which is the P3 format. So anyway, a little experiment that you can do if you want to check if your homework's working is actually see if some program can import your P3 or P6 images. And that's a really nice way, or just to compare if you write out a blank canvas what the file is. Okay, so you have a little way to check here. Okay, GIMP's a great free program to do that as well. Okay, so anyway, that's enough about the P6 format, and you get the idea about the binary data there. Okay. So just some asides, ppm is a pretty popular format. There's lots of cool tools you can play around with on Linux, so that's how you can look them up with this command if you want to see all the ppm tools, or a bunch of them at least. Now in practice, for your assignment, and we'll get to the assignment shortly at the end of the lecture, this is what you're going to have some sort of data structure, or maybe a function, depending on what language you're using, if folks are using JavaScript, where you need to store sort of in a collective data structure. If you're just doing C, then this will be a struct, and you'll kind of work with things in different ways, but where you have at least the width and the height of the image and the pixels, okay? And you might have other information that you want to store, such as the magic number, or comments, or, is it a 32-bit format? Is it floating point? Some of these other things, but minimally, this is what we're going to want. Some sort of structure where you have your pixel type that you're storing, although you could just store these individually. And this could be some sort of array or vector or whatever data structure your programming language offers, or in the standard library. And then the dimensions. Those are the main things that you're going to need. Okay, you can probably assume for the most part in this class, the range is going to be from 0 to 255 for images, but again, those are some things to keep flexible. If you're just reading in ppms, that's fine here. Okay, so this is what your sort of image format looks like, and there's a little sample again in the GitHub repo if you want to take a look at that. All right, now a few other issues to address with images, again, is sort of compressed versus uncompressed. I mentioned this a little bit in some of the different formats that we have, but in this course we're going to be working with uncompressed images, which means they're lossless. So if you compare this portion of the image with this one, a lossy or compressed image, this one's much more sharper. And maybe you don't initially notice it, but when you start looking at the actual stick and the details, or the wings of this dragonfly, you can start to notice what some of the differences are. This one's obviously a lot more sharper. And then when you add the things like the gamma correction and so on, you can actually see a pretty good image here on the left side. So we're not going to mess around with compressed images that are losing data, although that's something that you may look into. It may be something that can improve your iteration time when it gets time to actually generate images. So anyway, this is just a distinguishment between compressed and uncompressed image types. Okay. All right, and then there's a lot more on image formats, so I've just left a few notes here. This is actually something I worked on a little bit at Intel, just video encoding. There's ways to store, instead of RGB, sort of BGR. Sometimes your televisions will actually store the pixels in that order, so you'd have to consider those things. Sometimes you'll see the different formats that have the color channel and how many bits are stored in that channel. It's sometimes you're only storing say 16 bits, so you have something like RGB 565, and there might be one leftover bit maybe for the alpha, or it's just unused. So you'll see a bunch of these different types of formats here, depending on the device or environment that you're working on. But for us, it's just an RGB image, or RGBA with the alpha channel. Okay, so just something to keep in mind. As an aside, I considered the TGA image format. So there's some notes here if you want to read about it, or as an exercise, support the parsing of this type of format. But ppm is really the simplest for us. So That's going to be our goal, to just use the TGA image format. Or excuse me, the PPM image format. Yeah, this format's a little bit more complicated, and it doesn't align with the goals of learning more graphic stuff. We'll just get frustrated parsing images, which you don't want to do. Okay. Now, another sort of aside is, are TGA and PPM images good enough? Well, I'll go ahead and let you pause and take a moment to look at these 3 images and see if you notice anything different. So if you pause and take a moment to see what's different with these images, the actual difference is there's something called high dynamic range. Okay, so we can actually, depending on the format, you might want to store different things, like using actual floating point values for the pixels, for instance, or more bits per color channel. So these are different things that we can do to represent wider ranges of values. And the image on the right is actually the high dynamic range version, where you have lighter lights and darker darks. Is one way to think about it. And if you look at this carefully, I'll actually say that this image on the right is much more, it's much better. Okay, so here's sort of the image where you have the high dynamic range. Here they sort of darkened it here. And then here they have the high dynamic range image, so the original one, but they've made it darker. Okay. So again, what this is doing is it's preserving those sort of darker darks. It's not just taking an image and applying a filter to it, but it's actually just using the a larger range of values that can be stored. Okay, and there's a particular format for this called OpenEXR that was made by a company called Industrial Light and Magic, ILM. Maybe some of folks have heard of them. But you can really tell the difference with HDR on versus off. Maybe you've seen this on different phones, but again, the image on the right here, you can see that you can actually have the sun here and the clouds and so on, versus the image on the left, everything just kind of bleeds out here. All the pixels just appear white because they're too bright, and you can't have different levels of sort of brightness. It just sort of maximizes. So that's the difference with the HDR stuff, okay? So you can see it in a couple different images here. And basically what it's doing is, with a standard definition, you have a smaller range of colors, and you sort of map them to the color spectrum here. With HDR, you just have a larger range of colors here that are stored, and the mapping is much more precise here, okay? So this particular format, again, this might be a good candidate for final project stuff, to look into this type of library, for your images that you generate, and generate some cooler images, and then show the difference here just in the image format. Okay. So anyway, just a note on that, and then a little aside about Industrial Light and Magic. You should know who they are. Just some industry knowledge as you get sort of immersed in graphics. They have a whole history all the way back to the 70s, and they're sort of a powerhouse when it comes to doing graphics and the best stuff. I think they've done these movies that I just found on their website, but most things where the effects have been really cool have been noted here. So I've just got this image here because Space Jam 2 is coming out, and that's one that was interesting. All right, so Industrial Light and Magic's one worth looking out for, and we'll probably see them pop up again. Okay, so anyway, for this class, PPM images are plenty for us. All right, so if you need to, go ahead and give yourself a little 5-minute break. We just have a little bit of wrap up to do, and then talk about the homework assignment, and then we will finish things up. All right, and if you've given yourself a little bit of break, if you needed it, let's go ahead and continue on. Again, as I mentioned last time, these lectures online I can probably do in half or a third of the time as the full 3-hour lecture, but it's still good to always give yourself a little break here. Okay, so a few math notes that I wanted to make. As we're preparing, for our next module, we'll actually get into doing some graphic stuff, but just some terms, scalar values. Again, just when I say a scalar, I just mean an individual value, integer, float, double, these types of things. So here's a float in C++, and sometimes you can indicate that, yes, you want it explicitly a float by putting an F suffix at the end. And for most graphics applications, especially real-time graphics, floats are going to be enough for precision. Doubles might be too heavyweight, maybe not. For this class, I think we can consider using doubles just to get the precision. I'll probably go back and forth with that. But one thing to keep in mind with floating point precision, and I want to do this actually as a little live example, is to be careful with comparisons. This is going to come up sometimes in this class here. So let me open up an example of precision here. And what I've got here, let me actually just compile it and get ready to run it here, is on the left side here, just an example where I create two doubles, so numbers that can hold floats here. Okay. Then I've got this other thing called epsilon that's just sort of the margin of error. Okay, so I'm going to do this experiment here where I'm just comparing A and B. If you look carefully, these numbers are the same here. And I just want to know, for this first experiment, are they equal? Okay, and then I'll do the same thing again. I'll say A minus B. So this value minus this value, it should be 0. And 0 is less than this epsilon value, this really small number. So, they're still equal based off of these two comparisons here. Okay. But what I'm going to do next after that, so experiment 2, is do sort of a repeated multiplication. Okay. So I'm going to do A equals 0.1 times 11, something kind of weird here. And then I'll set B equal to 0, but then let's sort of simulate that over time as our program is running, we have this other value B. And, if my math is correct here, if I add B to itself 11 times here, it should be the same result as 0.1 times 11 here. Okay, so I should get this result that says, yes, they're equal, right? Because A would be equal to B. It doesn't matter how you got to this operation, right? It shouldn't, but we're going to see if they're equal here in experiment 2. And then I'm going to do the same experiment, but this time use the comparison with this epsilon trick where I subtract the result of A and B and just see if it's less than some threshold. Say, yeah, maybe there's some imprecision in our computers, right? They can't represent every single number that exists, right? Our machines have finite amount of space. But if it's close enough, they're probably equal, okay? So anyway, let's run this experiment. Compile it, it runs, and experiment 1 passes. Okay, so just to remind you what that is here. We set these two values, check if they're equal, we do our little epsilon trick in both of them, say they're equal. But experiment 2 fails, where we have this repeated multiplication here. Okay, and I even print them out too, like A is equal to 1.1 and B is equal to 1.1. And actually if I use C++ and send out some more of the precision, you'll see that there's a little bit of inequality between them. At the maybe it's a 12th digit or something, 12th significant digit, but these should be equal, right? But what I have to do is use this little epsilon trick here anytime I'm comparing scalar values that are doubles. Okay, so this is just something to be aware of. That you'll have to set up some sort of precision here, okay, to determine when things are equal. In the second case where I use the precision trick, I do show, in fact, that these are equal. So depending on your language that you're using, you might have to use this trick. It's just a little gotcha. And as we accumulate results here, this is an accumulation error, okay, where over time, as I perform more and more sort of math operations on high precision things, error accumulates, okay, whether it's in the 12th decimal place or wherever it is. And that's just something to watch out for, okay? So I'll just make a note here. Let me see, maybe make it on the next slide. Yeah, I'll make it right here, just so you can get the point here. Be careful. Error can accumulate. That's why we use epsilon here, okay, to sort of give us our sort of threshold for how much error we're going to tolerate before we in fact say, yeah, actually these numbers aren't equal. Because there is a difference between 0.01 and 0.001. That's reasonable, but by the time someone thinks 0.000001 or maybe 10 more zeros here, or whatever threshold you want to create, usually to 6 or so digits is fine. then you'll know if things are equal or not. Okay, so again, just something to keep in mind in a math thing that I wanted to talk about that maybe you weren't aware of and will come up in this class. Okay, so some other things, math-wise, just a few things. I've been talking about points and pixels and using just a Cartesian coordinate system. So that's where you have your x and your y here. That's going to get flipped later. We'll talk about that later. But this is 12 on the x-axis and 5 on the y-axis, so just something to keep in mind. This is called the Cartesian coordinate space. And this is a handy way, I guess, to represent pixels or to think about them. So again, just something to keep in mind here. And then we have points in coordinate space, in our Cartesian coordinate space. So we could have a third axis here, a z-axis, okay? So just also something to keep in mind, the x, y, and z, and where a point falls here, okay? If you need a little bit of practice here, there's a little bit of a game here where you can, click on the target here. Let's see if I can get it right, 6 and 4. Okay, so, just to get a little bit of practice there if you're warming up on your math stuff. Okay, so anyway, let me summarize this, give you a summary in your homework tips. We've learned about color, light, and image formats in this lecture, so you can review it as often as you like. And then a little homework tip is to use a tool like GIMP to help check your generated images. So with that in mind, let's wrap up by looking at your homework. So what you're going to be doing for your homework, and again, this is pushed to your repository, make sure that you add that, is creating a little ppm library or a ppm parser. And in the language of your choice, you're going to be reading in ppm files. So there are some sample files in this folder here that you'll be able to read in. And if you actually dive into them and view the raw files here, let me see if I can load one up, you'll see how they're formatted. But you'll need to be able to parse this data here. It's going to take a little while for that to show up. But you're going to parse that data here. So it'll be either a P3 or, well, the inputs will all be P3s, I'll tell you that. But what you'll do is you'll either lighten or darken that image, and then you'll output that image to a new file as described here. Okay, so you're going to output it, then it'll be either in the P3 format or the P6 format. Okay, so it'll be like this, and you can sort of mirror this format. Here you can see all the individual RGB pixel values here, RGB, RGB, and so on. So that'll be one of the tasks, and you'll get to kind of play around with the pixels, lighten them. By lighten them, I mean having the original intensity values, and by lighten, I mean doubling the RGB values, and darken having the RGB values, okay? And then the fifth image that you're going to output is just going to be a simple circle here. So if I just go into GIMP here, all I want you to do is, and let me grab this, is you're going to output an image, whatever dimensions you want, I don't care, and then draw a circle on it somewhere. Towards the center is fine, because I just want to know that you'll be able to have some control of creating a little library where you can draw shapes. If you want to draw something else on it, that's cool too, but at least a circle. So you can do a little bit of investigation on the formula for a circle, and that will get you sort of started or ready for the day, okay? And again, for this assignment, you can use whatever programming language you want, but I just need to be able to run it on the command line. So if I have it in C++, I just run it like such, whatever your program is, and the input image, and then it spits out the 5 images that are named as follows here, okay? Same thing for Java. I should be able to compile it in some simple manner here. If you use JavaScript or Python or whatever language you choose, again, it doesn't matter to me. This is what I would like to see, okay? And you'll describe how to run your program in this run.md file. This might be a very trivial instruction, but it gives me some instruction of how to run your program. Again, pretend like I don't know anything when I'm running your programs, and that'll be useful to you to make sure that I can run your solutions, as well as just in the future when you think about how you distribute software. It's always good to write good directions, okay? So that's what the assignment is. It's familiar to former students in a way, but a little bit different. And for other folks, it'll get you used to working with PPMs and the first part of what we need to do in this course, which is, to output images, because we're going to start drawing very soon. So I hope you enjoyed this one, have a good time until we see you next time. All right, take care.